But we have, I'm the president, I'm Gary Wilson, and anything goes wrong, you can blame it on me. We have Pat over at the door, and she is handling our merchandise. She's our merch manager. We have quite a bit of merchandise that we sell. If you're interested in any of it, we don't have it here to show you. But you'll come out here and tell people about it really quickly. It's on our website.
I guess I can go home because Jerry just told you everything I would have said. Thank you, Jim. Good evening, everyone. Usually there'll be a slide up there with some of the items that we sell. We are getting out of the clothing and business, so I have just limited sizes. I have short sleeve, long sleeve, sweatshirts. I also have carry bags, tote bags, and mugs and caps. So if any of those ring your chimes, let me know. I'm at merch manager at SBAU.org. That's MERCHMGR. And also a note to the club members, there are name tags over there, so let me know. I'm doing this for the secretary. Let me know if I misspelled your name, put too many H's or too many S's in it or whatever. So, back to you, Jim.
Thank you, Pat. I guess we can go directly into the outreach. The main focus of our club is public outreach. We go to support our local schools with their science nights, and local hotels used to be in the past. I don't know if we're doing any now. But go out there with our scopes and show them the night sky. And that's Chuck, our outreach coordinator.
Thanks, Jerry. Hi, everybody. You're famous. Okay, so we've already done almost 1,000 people so far at the beginning of March because schools have learned to stick their science nights before the time change. And coming up, as far as schools, we have 3 more, or 4 more before the end of the month, plus the Santa Barbara Science Fair to go help judge out with that. But our next public event is here, second Saturday of the month. It's usually our star party at the museum, weather permitting. That's starting at 7:30 and we go to 10, so hopefully we'll have good weather and lots of good stuff to show. Then third Tuesday of the month is Coming Around Marketplace for Telescope Tuesday. There's a lot of lights out there, so we try to make sure we have a lot of first quarter moons in the year, so that Tuesday moves around. But for this year, it's third Tuesday. Then on Friday, the 20th, is the third Friday of the month, is our public telescope night at Westmont College. And otherwise, it's all schools, so we don't have too many wide open public events going on. But there's always all kinds of stuff at the museum here with the planetarium, and then I guess it's on Mondays now, or Sundays? Sundays is the observatory is open for solar observing. So come on out and see cool stuff. There's all kinds of propaganda down here, star maps, moon maps, webpage listings, and bookmarks, and little join the club forms that you can fill out if you want. So thank you.
Thank you, Chuck. Now, if you had come out here almost 2 weeks ago to see the sun, because we have several solar telescopes on Sunday set up, they show sunspots, and 2 of them are hydrogen alpha, so they show prominences too, and you don't have to wait for an eclipse. But if you came out, as about 500 people did, to view the sun 2 weeks ago, you would have been disappointed because the sun was there, but there was nothing on it. No sunspots, no prominences, nothing. It's very rare. There were prominences, oh, excuse me, there were no sunspots. Okay. So that's very rare. It only happened once or twice that we know of in previous years. So, but right now, the biggest sunspot group has rotated around. It takes about a month for the sun to go around once. And so there's a lot of sunspots on now. So if you come out Sunday afternoon, it should be pretty exciting looking at the sun. Now we have an event planned, and the museum advertises that as starting at 7:30, and that will be our speaker. And I'm going to introduce our vice president right now, who's going to introduce our speaker. He's the one that finds and coordinates our speakers. And for the people that followed the museum's advertisement of the talk starting at 7:30, we have 8 more minutes. So he's got to stall.
You can take the boy off the radio, but you can't take the radio out of the boy. Okay, let the record show we're somewhat early as far as the speaker, but thank you very much for coming. You're here at the monthly meeting of the Most Fun Club. I'm going to make it the West, not just this town. It's because it's the fun science. As you all know, there's only one science that gets more news, and it's not as fun. It's called health and science, or health and medical, pandemics and whatnot. Boy, when launching the new NASA probe, boy, I tell you, we all love it. And I've been in the club 8 or 9 years, even when my last radio show, where I invited the guys in from the local astronomy club, and we met every other weekend, or every other Monday morning. And that became so important to me, to kick this stuff around, that when I ended my career, we decided to keep it going. So we have a vlog, a podcast vlog on Monday mornings. And doggone, if you want to have some fun with us, there's 5 of us now left on the screen. 11 a.m. It's called the SBAU Astro Hour. You'll probably see something about it here. And we'd love to get you to join. Here's what I like to do real quick before I introduce my speaker. And our speaker is an incredible lady who knows all about volcanoes throughout the solar system. I met her, very friendly, very knowledgeable. And she's sitting there with a gentleman named Uli, who we welcome from Germany. But for the rest of you, I want to know who's first-timers. Newcomers only, raise your hand if you want to know if you're here in the center section. Okay? People that have been here before, 2nd or 3rd, but you're not in the club yet. Ah, we did something right. Got your back. Now, members of the club SBAU. All right. Fantastico. I was going to take a little poll on behalf of the publicity department to find out maybe where you heard it, your newcomers, Newshawk or Independent or Ed Hat. Or...
Explorers Club.
Do they meet here?
Sometimes.
Are you an explorer? We're going to go for a hike later, maybe you and me. Let me run down some of the future speakers real quick. Since I was going to mention a bunch of names of people in the club that you would know, get to know, and become your friends if you decided to join. A month from now, Friday, April 3rd, Dr. Matt Malkin, distinguished professor I've been dealing with down at UCLA, speaks on what's new from James Webb. The astronomy revolution starts now. I'm sure it's been posted here. A friend of our speaker tonight, Dr. Abigail Freeman, F-R-A-E-M-A-N, also at JPL. On May 1st, we'll speak about her specialties, rocky inner planets. She's an expert on NASA's Curiosity rover on Mars. June 5th, potluck has been moved to June 12th. Instead of not having a speaker on the first Friday of June, we're going to meet in here and eat. See, if you join, you can go buy something like I always bring chicken. And then Dr. Aldana will talk about ancient Mayan astronomy in early July. So, where the hot stuff is, ladies and gentlemen, Volcanoes Beyond Earth. And she obtained a Bachelor of Science degree in astronomy and her Ph.D. in planetary sciences from University College London over in the UK. Her research and expertise is in planetary geology and volcanology. She studied Mars, Io, and Titan, as well as volcanoes here on Earth, received the Carl Sagan Medal from the American Astronomical Society, the Ambassador Award from the American Geophysics Union, and 2 NASA Exceptional Public Service Medals. You want to start your trip up here, my dear friend, Dr. Rosaly Lopes from Propulsion. We will take Q&A afterwards. Occasionally somebody wants to say something, you can be my guest.
Yes. Thank you so much for that introduction. Thank you to my friends, former JPL colleagues, friends from the Explorers Club, new friends. And thank you to whoever did this PowerPoint, because they are advertising my books. But now we have to switch to the real PowerPoint. Let's start. Okay, so I put volcanoes on the Earth and the solar system. Sorry, I changed the title a little bit, but particularly because I knew several of my Explorer Club colleagues were coming, I thought they would like to see some stuff on Earth, adventurous stuff. This is one of my favorite volcanoes. It's called Yazoo on Tana Island in Vanuatu. It looks dangerous, but usually it isn't, because this type of activity just has small explosions with fragments of lava that we call bombs. They don't actually explode, but they just land. And one of my trips there, in fact, my first trip there, I was with a couple of friends who live in Vanuatu, and another friend who was a photographer, and he said, you know, you should have a picture of you with the volcano, you know, exploding in the background. And I said, yeah, I don't have any of those pictures because I don't usually turn my back on them. And so we're there taking pictures, and suddenly there's a bigger explosion. I actually feel a shockwave on my back. You know, I turn around, and there are bombs actually flying beyond the rim. And so I said, don't run, look up, and this is how I was taught. You look up, you see where they're coming, and then if they're coming towards you, you just jump to the side. But they actually landed beyond us, and a really big one landed, you know, over a yard, a meter in diameter. And it was actually very useful because it had been raining, and you know, jackets got wet, and we were able to huddle around that bomb and put our jackets on the bomb to dry. So that was very useful. But anyway, and by the way, this is one of the easiest volcanoes to visit. If you get to Vanuatu, to Tana Island, you can have someone drive you, you know, nearly to the top, and then there are even concrete steps that you can take up to the crater, and there is even a park bench. The last time I was there was. So it's a very friendly volcano. But let's talk about volcanoes in the solar system. Volcanism is a fundamental process on planets. So we have volcanoes in many places. Those of you who were at the planetarium show heard, you know, and thank you for giving some of my talk. It's that we have volcanoes on Mercury, Venus, Earth, Moon, Mars, Vesta asteroid, Ceres, another asteroid, Io, moon of Jupiter, several icy moons of the outer solar system, and likely on exoplanets, that is, planets outside our solar system. I can't talk about everything, so I'm going to talk about some. And Venus, Earth, Io, and some icy moons, actually the underlying places are the places where we know there is current activity. For example, Mars, we know that there was activity in the past, but not now. And this is a picture of how lava fountain, and it's about 30 feet high. They can go much higher. Kilauea is having some wonderful eruptions at the moment. I was there recently, but unfortunately, between these episodes, so the volcano was mostly quiet, just a little below. That's a representation, not to scale in terms of distance, but the sun and planets. Yeah, I have a pointer. Let's see. Okay. So, as I said, volcanism is a fundamental process. Is what allows planets to cool. We have 4 major processes in geology. We have volcanism, here another Strombolian eruption. Tectonism, which forms mountain chains and also earthquakes. We in California know about that. Impact craters. Here you have meteor crater in Arizona, and erosion. And here you see an example of erosion on Earth. So when you look at the Earth and the Moon, they look so different because the interplay of this process is different. So on Earth we have a lot of erosion because we have wind, we have water. We actually have plate tectonics that just wipes away, erases the old crust of the Earth because you have one plate going underneath the other. So we don't see many impact craters on Earth. We see a number of volcanoes, most of them under the ocean. But these are the fundamental processes. So where are the volcanoes on Earth? Well, here are the plate boundaries. So we have these tectonic plates that are either spreading apart, like in the Mid-Atlantic Ridge, or coming together, like in the Andes, for example. And you tend to get volcanoes and earthquakes along these plate boundaries. So, for example, here is Iceland, and you have several volcanic islands in the Mid-Atlantic. Lots of volcanoes, Central America, here the Cascades, and then some interplate volcanoes like Hawaii. But this is where the volcanoes are located on Earth. Now, one very interesting thing about comparing the Earth with the planets is that the Earth is the only place where we know plate tectonics happens. We have not seen plate tectonics, any signs that plate tectonics is active on any other object. So there are different types of volcanic activity, on Earth, and this is very important to know if you want to visit volcanoes. Geothermal activity, like in Yellowstone, Iceland, great. Hawaiian and Icelandic eruptions, again, great to visit. This is a lava lake in Ita-Ali, Ethiopia. It's about, 300 feet across. Great place to visit. Strombolian, this is an example. This is Mount Etna, one cone on the side of the volcano. Small explosion, like I mentioned in the first slide, in Vanuatu. Again, pretty easy to visit, and quite safe if you know what you're doing. But then we start getting to the nastier ones, Palaeon, Vulcanian, Plinian, Ultraplinian. This is an example of a Vulcanian eruption on Mount Etna at the summit, and I'll show this picture again later. And this is Mount St. Helens, 1980, an example of a Plinian eruption. Now the names come generally from the places where the volcanoes are, this type of activity is common. Hawaiian, Icelandic, Strombolian from Stromboli Island in the Aeolian Sea, Palaeon from Mount Pelée, Martinique, Vulcanian again in the Aeolian Sea in Italy, that gave the name to all the world's volcanoes. But Plinian and Plinian, which are very explosive, nasty eruptions, they were named after a man, and the man was Pliny the Elder. Pliny the Elder was a general in the Roman Navy, and when Vesuvius erupted and sent nasty pyroclastic flows to Pompeii and Herculaneum, he tried to rescue people and he died during the eruption. But his nephew, called Pliny the Younger, was able to stay at their house, which was a safe distance, and observe the ash cloud, and he described it very in great detail in a letter to a Roman historian. He was really talking about how his uncle died, but that's considered the first scientific description of a volcanic eruption. So that's why it's named after the uncle, but also the nephew. So these different eruption types produce different landforms. So the Icelandic eruption sometimes is just like a sea of lava. You don't even see a proper volcano. Hawaiians tend to have these shield volcanoes. There are lots of lava flows on top of one another, and the name actually shield also came from Iceland because they look like warrior shields on the ground. Then Strombolian, they are a bit more explosive, and because this ashen material, scoria, falls close to the vent, they form steep-sided cones. And then the same for Vulcanian, Pellaean, and Plinian and Plinian. So the classic Fuji shape of volcano is only one type, and if you just look at the shape of the volcano, it gives you an idea of what type of eruption it predominantly has. And that's important in planetary studies because a lot of the time we just see the old volcanoes, but then we have a pretty good idea of what the type of eruption was, and also some idea of the type of rock, because these are common types of rocks on Earth: basalt, andesite, dacite, and rhyolite. And the type of rock has a great influence on how explosive an eruption is. Basalt is not very viscous, not very sticky. For the chemists out there and geologists, it has less silicon dioxide, SiO2, than the other types. So the gases that are dissolved in the magma and want to come out as the magma rises to the surface, they can come out easily. So they make like this whooshing lava fountains that you see in Hawaii. And then when you get to the more sticky lavas, these gases want to come out, but they can't because the bonds are so strong in the rock. So eventually the pressure gets so great that they just explode and the lava is fragmented. So that's what causes those really nasty explosive eruptions. Now, here are some examples, just pretty pictures. Hawaiian and Icelandic eruptions. This is a fissure eruption in Iceland, lava lake in Hawaii, Hawaiian flows going into the ocean. When this happens, there are boat tours you can take and take nice photographs, and some lava fountains that are really, really beautiful. So those are the types of volcanoes I recommend if people want to visit volcanoes, and also the Strombolian ones. Here is Stromboli in the Aeolian Islands, the Summit Crater, that's a group I was with. You just have to stay out of range of these bombs. My Ph.D. advisor taught his students that because he would send us in to collect samples. Because, we were expendable, graduate students. Now, here is in the Yazur in Vanuatu, that volcano that I showed in the first slide. So that was on another trip. We're looking down into the crater, and there are a couple of vents. And these photographs were taken from a plane. I was telling my friends when I met them earlier that a colleague of mine, we were flying between these islands with relatively small planes, prop planes, and she got chatting to the pilot, and it's like, oh, here again, and the pilot asked, is there anything you want to see on the way back? And I said, can you fly over the crater? And he said, yeah, it's not on our route, but we can do that. And so it was great. And he also said, oh, there was no door to the cockpit. And he said, well, when you get there, just get up and come here to the cockpit, and we'll open the window so you can take photos. So that's just one of my photos out of the window, and I was terrified I was going to drop my iPhone. And my friend took one with an infrared camera. And this, I'll stop. Okay. So, yeah, so you heard there's this whooshing of gas, and so there's a Yazur in Vanuatu. But then, we get nastier Vulcanian activity. These are on Mount Etna. And you notice the person here? Well, this picture was taken by a friend of mine, a colleague, who was there when Mount Etna started having this explosive activity and started getting larger and larger, and eventually they did what you're not supposed to do, which is just run down the mountain. And Calais eruption, Calais, Martinique. This is what it looks like today. We had a really violent eruption in 1902, and it destroyed a whole city called Saint-Pierre. And if you go to Martinique, you can still visit Saint-Pierre and visit some ruins and an interesting museum. Saint-Pierre was destroyed by pyroclastic flows, which is the same thing that happened at Pompeii and Herculaneum. Pyroclastic flows are these nasty mixtures of gases and ash, and they kill anything in their path. This is like the nastiest death possible. And they can be so light that they actually go over water. So that happened also at White Island in New Zealand some years ago that some of you may have heard the scene on the news. So this was from the eruption of Soufrière Hills in Montserrat that was taken in '96. The eruption actually ended up lasting quite a long time. And the Plinian eruptions, we all know about Mount St. Helens, and that was not only a very violent eruption, but it blasted out the side of the mountain. And the mountain had been evacuated, but unfortunately the volcanologists were expecting the explosion to go up and not sideways. So there was an area that wasn't evacuated enough, not large enough. Okay, so let's go to the moon. There are dark areas which were, like 3.5 billion years ago, there were seas of lava. The moon was still cooling, and there were very vast seas of lava. Where you see the bright regions, those are very cratered regions called highlands. And that's material that was ejected from the impacts. So the moon has no atmosphere, no erosion, so you can still see these very, very ancient surfaces. And then here is another image. This is Mare Imbrium, seas of lava, and you can just about make out the lava flows. And this is a lava channel. Apollo 15 landed. And the moon has a few quite small cones, so we did have some more explosive activity, but not a lot of it. I mean, this image is about 80 kilometers across, so they're like 10 kilometers or so across. So mostly Icelandic type eruptions, these vast seas of lava. Venus got a couple of people here who worked on the Magellan mission, and this is a composite made from Magellan radar data. Venus has a very thick atmosphere, so you can't use a camera to look through the atmosphere, you use radar. So Magellan was a radar mission, and here is a show volcano with a lava flow. And it's a computer-generated perspective, and it's got some vertical exaggeration, so we can see it better. Venus also has some what we call patera, which are like calderas, and it's got some domes that got nicknamed pancake domes, because that's what they look like. And this happens when you have quite viscous lava, but not much gas. So because there's no gas to really make those big explosions, the lava just comes out like toothpaste. In fact, in some places it's nicknamed toothpaste lava. So they form these domes that nicknamed pancake domes. And I have a friend who's an artist, Michael Caro, who's a space artist, and so he paints images of the planets and what, like for example, an eruption from a pancake dome might have looked like here in the very thick atmosphere of Venus. And this is a fracture. And he usually talks to scientists like me. That's how we got to know each other. To make sure he's getting things more or less right, but it's an interesting perspective, and it's very interesting to work with an artist because they'll ask you like, well, what would you look like if you were actually there? And they said, well, I don't think that way. I just look at data. So it's a very different perspective. Well, years after Magellan, there's another volcano called Mat Mons. There's a vertical exaggeration of 10 times so that we can see it better. But some colleagues reanalyzed the Magellan data, and they found a region that had changed. There was a new flow, compared, and this vent looked different, like it was expanded, so we realized that really volcanism is still happening on Venus. There have been several clues and hints, but this is really what proved it. This type of analysis that they did with these radar images was not possible at the time of Magellan because we just didn't have the computing power to do it. So going to Mars, Mars has the largest volcanoes in the solar system. This is a map based on altitude, and here is Olympus Mons, the biggest volcano in the solar system, like 600 kilometers across, and these are called Tarsus Montes. Those of you in the planetarium already heard about them. Mars has, again, areas that are very heavily cratered, and some areas, particularly in the northern hemisphere, that have less impact craters, which means they are younger, because the longer a surface is exposed to meteorite impacts, the more craters it's going to have. So here's Olympus Mons, and actually that's the first volcano I studied for my PhD, because might as well start with the biggest. And it's 26 kilometers high, which looks really high, but in fact is 600 kilometers or nearly 400 miles in diameter. So in fact it has quite gentle slopes. And here's some data from Mars Global Surveyor showing all these big volcanoes. These ones are only a little bit smaller. So my first project was to analyze this material around Olympus Mons that's called the Oriole material and the volcano and find a connection. Michael Carroll made this painting of a volcanic eruption on Mars triggering flash floods. Most of you have probably heard that Mars had rivers in the past, a lot of liquid water, and that's one reason why we think it's so good. It's such a good candidate for us to find life. And this is the book we wrote together, Alien Volcanoes. So we did lots of paintings for this book, which was fun. Someone did mention that Abby Freeman is going to come and talk about the rovers. So I'm just going to show here one slide from Curiosity. Curiosity found a lot of sulfur, these bright white clasts of pure sulfur, and it had never before seen on Mars. Sulfur is really associated with volcanoes, and the rover wheel actually crushed one of these clasts, and you can see the yellow inside, which is the more usual color of sulfur. So you find on Earth sulfur around volcanic regions, but also hydrothermal regions, and hydrothermal regions are good for life. So that was a good find. And here is a view of another rover. We have Perseverance rover and Ingenuity, a little helicopter that unfortunately is no longer flying. It flew a lot more than expected, but eventually it landed badly. But this was a really great thing that we did at JPL, and I mean, not me personally, but it went on the spacecraft not as a science experiment, but what we call a technology demonstration, and it demonstrated you could actually fly this little drone on Mars. And I have no doubt that in the future we're going to fly a lot more of these on Mars. And there is a mission being built at the moment to go to Titan and fly a big drone on Titan. Okay, one of my two favorite moons is Io, the one that looks like a pizza. I worked on the Galileo mission. This is a Galileo image of Io. So all the black areas are active volcanoes or recently active volcanoes, and the yellows and reds, and these are all sulfur dioxide deposits. So Io is really quite extraordinary. It has no impact craters, which means that the surface is really, really young, and it was nothing like anyone had seen before. And I worked on Galileo with an instrument called the near-infrared mapping spectrometer, and in the infrared you see the active volcanoes. The day side or day-lit side is kind of more greenish. The night side is in blues, but all the volcanoes, they just pop out and in fact saturate the instrument. We found some quite high temperatures on Io, which indicate that they are at least basalt, because different rocks melt at different temperatures, but they might be of a type of lava called ultramafic, which no longer erupt on Earth, but were very primitive lavas from hundreds of millions to billions of years ago. I would go around comparing pixel by pixel those images and, and finding, more hotspots. That's what we call volcanoes on Io, and it was very exciting. The volcanoes on Io were discovered by the Voyager spacecraft in 1979, but they were predicted. And the lead author of the paper, Stan Hill, was here at the University in Santa Barbara. So 2 weeks before the Voyager spacecraft flew by Jupiter and Io, they published this paper that they predicted massive heating of Io's interior due to distortions in the shape caused by the gravity of Jupiter and other Galilean satellites. So they said tidal heating expected, and even one might speculate that widespread and recurrent surface volcanism would occur on Io. And this was 2 weeks before the discovery, so it was really well timed. So what happens that these Galilean satellites discovered by Galileo, Io, Europa, Ganymede, and Callisto, they are in synchronized orbits, which means like for every orbit that Europa does, Io does too. So Io is being pulled in Jupiter's direction, Jupiter's big planet, by Jupiter's gravity, but at the same time, it's being pulled in the other direction by these other moons that are much smaller, but they're closer. So it forms a tidal bulge that is distorted. It's a bit like a tug of war between Jupiter and the other moons. And this makes the interior heat up, and that's what keeps the interior of Io molten and causes the active volcanism. That was also the discovery of tidal heating to allow even small moons, Io is the same size as our moon, to remain active long after they should have cooled. So the discovery was done not on a scientific image, but on this image, which was used for navigation of the spacecraft by a young engineer called Linda Morabito, and she noticed these plumes coming out of Io, so they are volcanic plumes, and then they found thermal emission and also sulfur dioxide in one of the plumes, so that was the proof that there was active volcanism. Anyway, Voyager found about 9 plumes, about a dozen active volcanoes. One of the biggest one is called Loki, and that's a volcanic crater, and everything that's black is actually hot lava. It's got an island in the middle, which is a bit mysterious. And Michael Caro made this painting of what the interior of Loki and this island may look like, if you were there peering over the edge. And this was fun. And then more recently we had the Juno mission, and this is that's still actually around Jupiter, and this is an image taken from Juno. This is this Loki volcano over here. These are tall mountains, and the camera on Juno was like a student project almost. It was not supposed to be a real scientific instrument. Juno was not supposed to get close to Io, but at the end of the mission, it actually did. I'm going to show here, this a movie made from some of the Juno images. So this is the Loki, this sea of lava, 200 kilometers across, with an island in the center. And in fact, we had found out what we thought Loki was from Galileo. This is one of my images, and this is in the near infrared, showing it's hot on the edge, and this is a thermal map. It's in Kelvin, but here is one in Hawaii. And what's happening here is that the lava lake forms a crust of lava. The lava pools forms a crust, but cooled lava is a very good insulator. So that means that the stuff underneath is still liquid and very hot. And so this crush starts kind of sloshing around. It's a bit like scum on a pond. So when it hits the sides, it breaks. And that's what forms these hot edges. And here is a camera image at night of one other volcano, and it just shows like this hot edge. And even in a visible image, this is a volcano called Tupan, about 70 kilometers across. Again, it has a cold island in the center, but everything that's hot is dark. And if you look around here, there's a dark line all around this island. It's almost like someone traced it with a pen, and that's where this lava crust is breaking out. And and here we see some probably sulfur coming down the walls. And Michael Caro did this beautiful painting. And it was our first collaboration. This is steep walls and sulfur coming down and forming these sulfur deposits. And I like this so much that I bought it from him, and it's in my house. And it's kind of fitting because I also named this volcano. I suggested the name to the International Astronomical Union. Tupan is the Brazilian nature god of thunder, and all the names on Nile come from gods or heroes that have something to do with fire or volcanoes or thunder. So it was a good name. And with Juno, I've been working with the GRAM is an instrument in the infrared on Juno, and we found many more places where you have these hot rings. So I was just full of them. Lots of lava lakes. Now, lava lakes are very rare on Earth, but they're pretty common on Nile. And so colleagues of mine and I started working on lava lakes, and one of the best ones is Ita Ali in Ethiopia. Not an easy place to get to, and it's close to the frontier with Eritrea. It makes it's a little dodgy. This is our path, and we went up the mountain. That's me. That's one of my colleagues. We were escorted by tribesmen, or actually they look like 16-year-olds with AK-47s, because it's a very tribal region and Eritrea is nearby. So that was an experience. This is not a photo by me, it's by one of my colleagues. It's just the most beautiful photo of this lava lake. And you can go right up to the edge, and it's really like being on the edge of hell. It was quite amazing. And I'm going to show you here a movie that we took. Let's see, yes. This is the wall, and you see it's breaking up against the wall. And you can see how quickly it starts cooling.
What's the approximate scale on that?
This would be about, maybe 30 feet, this area. We're using a lens, but the whole lake is about 300 feet across. And here we are on the edge. And this is in the infrared, because we use infrared to make temperature maps. That's, making temperature maps, we then, compare with temperature maps on Io. And another lava lake we went to was in Vanuatu, but on another island called Umbrium. And this is like a topographic map. It actually used to have 2 lava lakes. Unfortunately, they have collapsed. So, they are not there anymore. Maybe they'll come back. So, this is 2 planetary scientists, 3 planetary scientists, colleagues of mine. And we had to, make our way through, through jungle and, climb up with help from the locals. But, here the locals were unarmed, at least. And it was a much quieter place. And this is the lava lake, which it's around the same size as the one on Ita Ali, 100 meters, maybe a little smaller. And we're here looking down. But the difference of this lava lake, you see, it's even during the day, it's like all red, is that it's very, very turbulent. So it's unlike the ones that we see on Io. And here we have in the infrared, and you see just bubbles very violently. So very different from Ita Ali and the ones we see on Io. So picture of Io taken from another spacecraft, New Horizons. There are some plumes that go like 500 kilometers high. And this is another moon called Europa that attracts a lot of interest, and we have a mission going there at the moment called Europa Clipper. Well, why? It's not quite because of volcanoes, although it has what we call cryovolcanism, which is cold volcanism. So what happens? These icy moons, crust of ice, but water underneath, oceans of liquid water, and probably some volcanism in the interior. So here it's an exaggerated color, but you see a lot of cracks on the surface. And here are areas where we think the material from underneath came up. So that's called cryovolcanism because it's cold. The water is, the material is water, maybe mixed with some other components, but maybe is below 0 centigrade. It's probably some places the cryo lava would be like minus 150 Fahrenheit. So it's actually cold volcanism, but any process that brings material from the interior to the surface is volcanism. This moon here, Michael Caro did some drawings of what the interior might look like. There is some argument whether the ice crust is very thin or whether it's thicker, but not sort of solid ice. But likely it has some volcanism in the interior. And this material is coming up. Now, you have water, you have heat. We very likely have organic materials. So these are some of the ingredients you need for life. And that's why this moon generates so much interest. We know that on Earth we have a lot of underwater volcanoes, and in this like so-called black smokers, there's a lot of life down there. And these may well have been the places where life on Earth originated. Volcanoes eventually come up to the surface. This was Surtz in 1963, which was a new island formed off the coast of Iceland. And the island is still there. It can only be visited by researchers. I have never been there, unfortunately. I've only seen it from a distance. And then another very interesting place, I also worked on the Cassini mission. And we found, Enceladus is always a bit of a strange moon. It's quite small, like 300 miles across, with a very bright surface, with not many impact craters, which again tells you it's very young. And with Cassini, we found that these cracks near the south polar region were actually warmer, that's the infrared instrument, than the surrounds. And then the camera found that there are jets, essentially of water, with some hydrocarbons. This is exaggerated color, so you can see it. But these plumes coming out. And like Europa, you have ocean under the ice crust. You have heat, you have hydrocarbons. Another interesting place for life. Michael Carroll made this view of plumes on Enceladus, what it would look like if you were there on the surface. Inside, we think there is a global ocean, and the South Polar region is where there are these active jets. There is a rocky core, and what it makes it really interesting is that there's some silicon nanoparticles were detected by one of the Cassini instruments. And, from lab experiments, these dust particles must have formed on the seafloor at relatively high temperatures. And so these are pretty hot environments, so it suggests that seafloor hydrothermal activity is happening. And this is one of the reasons why we think that Enceladus is a really good place where life could have evolved. Of course, one of the biggest questions we have is, does life exist somewhere else? And I think I'm running out of time, so I'll go somewhat quicker, but my second favorite moon, or my other favorite moon, is Titan, so Saturn's largest moon. Titan has a very dense atmosphere. You can't really see the surface using a camera, so we use radar. Here are radar strips, so each time we flew close to Titan, we would get one of these long noodles. Underneath is an image taken with infrared that showed some detail. And by the way, my boss on Cassini, the deputy team leader of the radar, is here. So if you have questions about the radar, he can answer them. So we think that Titan has an ocean also under an ice shell, and the magma may be water or water ammonia. And does it have volcanoes? Well, we found a suspicious-looking sort of crater here on this radar strips. Radar data are kind of a lot harder to interpret than images, physical images. But we thought this looked like a volcano, and maybe this is a lava flow, and then there's a field of dunes. Titan has many dunes as well. And we were very lucky, it was not even from planning, but we got 2 radar passes that crossed over in a way that we could do stereo, or one of our colleagues at the USGS could do this stereo. So here is a digital terrain model, and it actually showed a very deep pit, over 1 kilometer deep, next to a tall mountain, over 1 kilometer high, and another feature at the end of the strip that also looked like a volcano. I got also some data from the infrared instrument that reveals some composition. These are artificial colors, but it shows, it's also exaggerated in perspective, but it shows that the areas we thought were volcanic actually have a different composition than the surrounding areas. And so that is a strong hint, and I'm going to show here a movie that is false color, but here is the pit, the mountain, the maybe flows. This is stereo mapping, and then it's going to change to topography or height, we never detected thermal emission from this volcano, so we can't prove it's a volcano, but it sure looks like it. This is very exciting. And here we have the field of dunes, and then at the northern end of this strip we have another possible cryovolcano. And maybe the next mission to Titan is going to show whether we indeed have cryovolcanoes. So volcanoes exist on many places in the solar system, maybe even exoplanets. There is one exoplanet that appears to have a very hot side and another side that's not so hot. And maybe not. It's a lot harder to work with data from planets outside our solar system, but we now know that thousands of planets exist outside our solar system. So there may be many interesting things there. And perhaps even an Io-like exomoon. This young fellow who's now at Caltech found a sodium cloud that could be created by volcanoes and was like obscured by the light of a star, and so he proposed that it could be an exomoon that was actually like Io that was creating these clouds. And so this is pretty much the end of the talk. I'm going to leave you with my favorite image from Cassini. This is Saturn with the sun behind it, and it shows all the rings and the beautiful glory. But there's something very interesting in this image. It's not easy to see, so I'm going to show it in the next slide, and this is the Earth. So I love this quote from Carl Sagan because it really puts things in perspective. It's like everyone you have ever known or heard of, has lived here. A really insignificant bit of dust. So I think that's a very good perspective. So with that, thank you so much for your attention. Well, you can pick them, pass the microphone around.
Yeah, it doesn't work.
Oh, it doesn't work. Oh, gee. All right, so shout.
Shout it out, you get to pick.
Jerry, turn the microphone on. You turn it on.
It's been turning on.
Are you sure?
Yeah.
It's been muted, so you wouldn't make noise.
Does it work now? Oh. There you go, Ron.
Oh, I get to run around the room. Thanks a lot. So that we can be heard, I'm going to ask, save your question. I get the president a lot. We're talking about fraternity.
Dr. Lopes, to what extent do you believe that volcanism on Venus is influenced either by an unconventional tectonic plate that kind of moves up and down, or if it's tidal forces from the sun and neighboring planets, which could also potentially explain volcanism on Mercury?
Okay, I have not heard about the tidal, hypothesis. It seems to me that it's a little bit too far away from the other planets and the sun for that to really work. Tectonism, well, actually suggested in the past that even had plate tectonics, and that is kind of not very well accepted by the scientific community, although it seems to be coming back now with, perhaps not. And so there is we're planning 2 new missions to Venus. And one of them, that's out of JPL, would really, explore those, tectonic features and the volcanism. So maybe then we'll know the answer to your question. I'm going to ask Steve, do you have any comment on this since you've studied Venus?
Who are we talking to? Who wants the mic? There are so many ideas about what the inside of Venus is like. I'm not a geologist, I'm basically an engineer, but maybe a geologist.
I just know you worked on my channel now. Oh, Thomas, yeah.
I think one of the main ideas is that it's basically a one-plate planet, and it's capped in the heat so that eventually, every once in a while, it pops through with these huge volcanoes. But there's no other way, there's no shifting of the plates to allow the heat to escape. So either it does that, or some wild ideas are that the entire planet, the plate founders and sinks into the interior. That's still pretty controversial, but the crater in history seems to indicate that that could be possible.
Thank you. This is Tom Fogg, retired from JPL, who worked on my channel. Hey, it's great to have friends in the audience.
I'm going to see if our president has a question. He normally does.
In your introduction, you had listed one of the planets as Ceres. And I remember when our space program orbited Ceres, there was a white spot in a crater. And I think that was claimed that it was salts that had evaporated on.
Yes, Ahuna Mons, I had a slide about that, but there were just too many slides, so I took it out. I'm not sure that I have it in the backups.
Would you call it a cryovolcano or?
Oh, yeah, here it is. Yeah, that's a suspected cryovolcano, about 20 kilometers high. This is 2 times vertical exaggeration. Yeah, and so that's another world that has or had an ocean underneath, and so pushed out that cryovolcano.
Mons is the word for mountain, right?
Yes, yes. It's a convention from the International Astronomical Union.
That one on Mars is a monster, I'll tell you.
Yeah, Olympus Mons. Hi.
Hey, you mentioned earlier, I think right around the start of your talk, that Earth is maybe the only or one of the only places that we know of to have plate tectonics.
Yeah.
I'm wondering what's abnormal or unique about Earth that makes that so rare, or do you think it's something that as we search more, we'll find more?
Yeah, hopefully as we search more, we'll find. There are several, theories about that. One is that you need the right ratio of the size of crust to the size of the planet. If it's too thin, like possibly in Europa, the ice crust, it just breaks up all over the place and plate tectonics doesn't really start. Other places like Mars with a thicker crust, maybe it tried to start, but you just can't move the plates. Also, if you don't have liquid water helps the one plate sinking under the other. So it's probably a combination of factors, but you need sort of like a Goldilocks thickness of crust versus the planet. It's not my expertise exactly, but this is, what I heard.
Dr. Rosaly, one of our proud members is here tonight. Professor of Astronomy up at City College, Dr. Sean Kelly.
Sorry. That's so fun. Thank you so much. It was a great talk. Lots of interesting ideas. I'm just wondering, because you teased with those pictures you just showed, you had a picture of Pluto, and I would just be really curious to know what's going on with Pluto. Why would you have that?
All right. Okay, so that's Pluto from New Horizons, and there are a couple of possible cryovolcanoes. It's good to have backup slides, right? Pluto is a place that's very, very cold. There are a couple of possible cryovolcanoes. One's called Wright Mons. It's really quite big, and if indeed it's a cryovolcano, it's actually the largest in the solar system. But again, a lot of the time in the space missions we find out so much that's new, and yet don't find out enough. There are always more questions.
Can I ask one more follow-up?
Sure.
What's the driver that would give it the energy to erupt?
Pluto probably tidal, because it's actually in a system with other bodies. And that's why Pluto's not a planet anymore, because it doesn't have others around it. It's in this strange configuration.
This will be in your Monday class, right, Dr. Sean?
Sure.
Okay. Somebody has a great question back here.
How do we know if there's no volcanoes on Neptune, Uranus, and other dwarf planets?
Neptune and Uranus are gas giants, so they probably have a solid surface, but it's way underneath, and most of the body is actually atmosphere. So whether they would have something resembling a volcano is really unknown at this point. The dwarf planets, like Pluto is a dwarf planet, Ceres, Vesta in the asteroid belt. So some of them probably have cryovolcanoes.
Who are you?
Alia,
Are you from Santa Barbara?
Lompoc.
Okay, you're
Great. Well, thank you for coming. A couple more here.
Pick one.
All right, he was first.
Is there a way of identifying volcanoes when we can't make direct observations, like in the cases that you showed, like where it's beyond our reach?
You can identify changes in the atmosphere, heat. In the case of that possible exomoon, is a sodium cloud. So there are ways. I mean, if you don't, sometimes it's sort of difficult, it's like that exomoon is possibly an exomoon, but it's hard to prove. Even for Titan, it's actually, we got good evidence, just from the morphology and topography and the what we can tell about the composition, but we don't have the, haven't quite, hit the nail in the coffin yet, because we didn't detect total emission or any changes. Like in the case of Magellan, when they detected changes on the surface, that was it.
Yeah, I wanted to ask a question about volcanism on the moon. Why does it appear that there was volcanism on the side of the moon facing the Earth, and the images and the data we have from the far side of the moon indicates that there wasn't? And I was wondering, what are the theories for explaining why volcanism ended on the moon when it did, and what are for some of the research for what is going on in the core of the moon and so
Yeah,
forth?
yeah, that's a very interesting problem and very interesting question. There are, a number of possible explanations, but none particularly satisfying. But what we need is seismic data from the moon, and in fact, we're building a JPL seismometer that's going to go to the far side, because the Apollo astronauts put some seismometers on the near side, but we really need that, coverage to actually say what's happening in the interior of the moon. It could have been just like a tidal effect of the Earth, but maybe something more complex or different.
What's the main reason NASA wants to know about volcanoes?
Well, NASA wants to know about lots of things. Volcanoes just happen to be my specialty. But we never did a mission to another planet just to find out about volcanoes. We go to find out about, the whole history, geology, atmosphere, the system. So it's sort of much bigger questions than just volcanoes. But if we find some volcanoes, that's great.
Back to you.
Over there.
I asked her earlier before the speech how we're going to land on one of the icy moons without melting or labeling.
So we have the only planet with plate tectonics. All these other volcanoes are existing on planets with no plate tectonics, so no subduction. So it's only the accumulation on the surface of material that's erupting from volcanoes, but doesn't over billions of years. Why is there no compensating ingestion, as subduction?
Right.
There has to be some equilibrium at some point.
Yes.
How is it possible to only generate surface without some form of subduction?
Oh, it doesn't mean that there isn't some form of subduction. It means that no plate tectonics is different. But, you have material can spread, the crust underneath may get molten, so there are possible processes. It's just this, what we have on Earth, this one plate going underneath the other, the plates, splitting apart. That's what we haven't seen on another planet at the present time, or, we don't find particularly convincing evidence that happened in the past. Now, some of the volcanoes on Earth, like Hawaii, are mid-plate volcanoes, so that just means that there is a hot spot, like a weakness in the crust, and the volcano just, punches up there. And some volcanoes on other planets, like Olympus Mons, is so large because it built there over a very, very long period of time without plate tectonics. It just in Hawaii, because the plate moves, new islands get formed, new volcanoes get formed. And at the moment, Kilauea is very active, but there is a submarine volcano that is, coming up. I think it's like in the next 100,000 years or something. It's going to become an island. So planning a vacation now. There was a question over there too.
Oh, halfway. Bring the microphone. I'll be there. Give me a minute. The only exercise I get.
Can you explain an ice volcano? Why would ice erupt? Is it a chemical gas?
Okay, well, these moons have an icy crust, and underneath they have liquid water, or maybe liquid water with some other things like, ammonia and so on. But I think what you're trying to ask is actually a very good question in cryovolcanism. Ice cubes float, right? So how come that you get that density difference between the liquid and the surface? Various explanations for that, about, squeezing things out. Maybe the crust is not actually pure ice, but it has a lot of dust, so it's not, the density contrast is not as much. Substances like, ammonia can change the density of the water. So there are several possible explanations. Again, none that we can actually say this is what happened there, unless we get, more local data.
One of our members, Mike Hardwick, you usually have a question? I'm out of questions. Mr. President.
Actually, a while ago, I had read something about planets mostly on the Earth's size, starting with differentiation. They became molten and all their heavy elements.
Was the same.
And then as they became liquid, then the surface, which was radiating into the 4 Kelvin background of deep space, that radiated heat away, and the surface, when most metals or materials, when they cool, they contract. And so the surface contracts, and that puts a squeeze on molten material underneath. And it causes the surface to crack, and it can cause volcanoes. So that's a non-plate tectonic thing that could produce that.
Yeah, yes, it's can also produce possibly like molten chains, like some molten chains on Titan. One of my colleagues proposed that it was exactly that. It was a planet contracting and pushing out these molten chains.
And the Earth has had a unique history in the sense that we were collided with by Theia. So we lost a lot of our crust to form the moon. And we were left with a thin crust. And we were left with then now a relatively large moon, because most planets are as large proportionally as ours. And that gives us our plate tectonics. So I think we're a little unique in that way.
Yeah, I think the Earth is pretty unique. Yeah. But then you start studying other planets and you go like, Io is unique, and Titan is unique.
Actually, because of that, I think there should be another term in the Drake equation. But that's another talk.
Oh, that's another talk. Yeah, I have opinions about that. It's one reason why it's so important to find if life started elsewhere is when you get to the last term of the Drake equation, you can't do statistics on a sample of one.
Thank you, excellent talk.
Question.
Yeah.
Are there any volcanoes in California, and are there any in the ocean?
Oh heavens, yeah, of course there are volcanoes in California. Lassen Peak, great place to visit. Long Valley Caldera, and in Mammoth, Mammoth erupted, when was it, 1700s? Remember? Yeah. What? Yeah, that's right. Shasta is still in California, right? I tend to get a little confused on these cascade volcanoes because they keep going up, but lots in Oregon, yeah.
They occur in the ocean.
Oh, the ocean. There is one, I think is off the coast of Oregon. I'm not quite sure. But we certainly have Hawaii. But yeah, there are volcanoes in California that could still erupt. They, didn't. Last eruptions weren't that long ago for Lassen and mean, there are photographs of Larsen Peak eruption. So like, 100, 120 years ago, something like that. Yeah, it's, so yes, we could still have eruptions in California.
And in the ocean also.
And I would rush out to see them.
The eye of the Jupiter, could that be like heated by like volcanic degassing thing?
I'm sorry, I didn't quite.
Like, do you think the eye of Jupiter could
Yeah.
be like heated by like a volcanic degassing like radiant on the surface?
If Io is the gassing?
No, like Jupiter.
Oh, Jupiter. Okay. Jupiter, yes, a gas planet, it's got all this, storms, coming up from underneath and so on. But I'm not quite getting what you're asking. Maybe I didn't hear it very well. Or are you asking about the Io flux tube? Maybe that material from Io is being implanted into Jupiter because it travels to the magnetic field?
There's no core in the Jupiter?
No?
No.
Yeah, there is a core, an interior, but we don't have much for fluids going on there.
This gentleman has a question.
Okay.
I think it should be simply, a question that could be answered simply, but I don't have, or I've never heard a good explanation for a mechanism that keeps any planet or moon warm enough over a course of 3.5, 4 billion years to allow for current volcanic activity. I can see that it showed up in the past, but even here, I mean, with the Earth being as old as it is, what is the mechanism?
It's tidal heating, like happens on Io.
Well, tidal heating, you're saying it's friction between planets and moons, right?
Yeah.
That might count for 300 million years.
Oh, it could last much longer than that.
It's hard to believe you get billions of years out of that.
You do count also radioactive.
Yeah, there's also, the radioactive decay.
Doesn't last that long either.
But tidal heating is what is keeping.
I don't know. I think science sometimes fools itself into believing stuff it doesn't have to.
Well, I gotta tell you, Dr. Rosaly, it's the first time I've seen the term exomoon, but I'm sure it's been around a while. I know they're having enough trouble finding and identifying and photographing the exoplanets, but the moon, are they actually moving down in distant galaxies? Or distant stellar systems? Exomoons.
Exomoons.
Yeah, moons that are not in the solar system.
Yeah. Well, there is no real hard evidence yet, but there is some very interesting work, like I showed, that is an indirect evidence of an exomoon. Not direct, because, direct evidence of something as small as a moon is quite hard to detect.
We got gifts for you.
Gifts, hey.
Your honorarium, right here. You're going to get back tonight. This is our official Cosmic Cup.
Thank you. It pays for the gas, as you
Something
said.
our official SBAU tote bag.
Thank you. Thank you so much.
Thank you for coming. I'll get to close the meeting now. We got not much time. We're going to be out here in about 10, 12 minutes at 9 o'clock. But get to know who you can on your way out and maybe come and ask a few more questions. See you next month for Dr. Malkin from UCLA. And thank you for coming.